Hydrogen storage for power systems. A practical guide with the growing need for clean and sustainable energy sources. Hydrogen is emerging as a promising solution to power our systems efficiently. Its zero-emission fuel properties make it an attractive alternative to traditional fossil fuels, while offering a versatile application in various sectors such as transportation, power generation, and industrial processes. However, to harness the full potential of hydrogen as a clean energy carrier, we must first find efficient and practical methods for storing it. This is where hydrogen storage systems come into play. In this guide, we will explore the different types of hydrogen storage systems available and discuss their practical applications for clean energy systems. We will also look at the advantages and disadvantages of each system and the factors to consider when choosing the right one for a particular application. Whether you are a student, researcher, or professional looking to learn more about hydrogen storage, or an industry professional looking to make informed decisions about your energy storage needs, this guide will provide you with valuable insights. Let's dive in and uncover the latest advancements in hydrogen storage technology together. Hydrogen's potential. A clean energy revolution before delving into the types of hydrogen storage technologies. It's crucial to understand why hydrogen is gaining so much attention as a clean energy source. Unlike fossil fuels, hydrogen produces no greenhouse gas emissions when used in fuel cells or internal combustion engines, making it an environmentally friendly option for powering our vehicles and appliances. Additionally, hydrogen is extremely versatile and can be used in a wide range of applications, from electricity generation to industrial processes, like steelmaking and cement production. By switching to hydrogen as an energy carrier, we can significantly reduce our carbon footprint and move towards a more sustainable future. Moreover, hydrogen offers several logistical advantages over other renewable energy sources, such as solar and wind. It can be easily transported through existing pipelines and infrastructure, making it readily available for use. Furthermore, hydrogen can be stored and discharged as needed, providing a reliable and flexible energy solution that can help balance the intermittency of renewable energy generation. These factors have made hydrogen an attractive option for governments and industries worldwide to invest in research and development for clean energy systems. Types of hydrogen storage technologies. Now that we've established the importance of hydrogen as a clean energy source, let's explore the various types of hydrogen storage technologies available. Each technology has its unique working principle, strengths and weaknesses, and considerations for use in different applications. Compressed hydrogen gauge. Compressed hydrogen storage is the simplest and most widely used method for storing hydrogen. As the name suggests, this technology involves compressing gaseous hydrogen to high pressures, typically between 350 and 700 bars, and storing it in specialized containers known as hydrogen cylinders or vessels. At these high pressures, hydrogen can be stored at ambient temperatures without liquefaction or chemical reactions. To use the stored hydrogen, it is released from the cylinder through a valve and can then be fed into a fuel cell or internal combustion engine to generate power. The primary advantage of compressed hydrogen storage is its relative simplicity and cost-effectiveness. Existing infrastructure for compressed gas storage and distribution can be easily adapted for hydrogen storage, reducing the need for significant upfront investments. Additionally, the technology is well understood and has been used for decades in various industries such as oil and gas. However, there are some challenges associated with compressed hydrogen storage. The high pressures involved can lead to safety concerns and require specialized equipment and expertise for handling. Moreover, the storage capacity of hydrogen cylinders is limited, and as a result, frequent refills may be necessary, especially for applications requiring large quantities of hydrogen. Despite these challenges, compressed hydrogen storage remains a viable and popular option for many clean energy systems, particularly for transportation and mobile applications where space and weight constraints are less critical. Liquid hydrogen, LH2, liquid hydrogen storage involves cooling hydrogen gas to extremely low temperatures, approximately negative 253 degrees Celsius, to liquefy it and then storing it in cryogenic tanks. At these low temperatures, hydrogen becomes denser and can be stored in smaller volumes compared to gaseous form. Once needed, the liquid hydrogen is released from the tank and allowed to vaporize, which generates a small amount of energy due to the Joule-Thomson effect. The resulting gas is then fed into the desired application, such as a fuel cell or internal combustion engine. The primary advantage of liquid hydrogen storage is its high energy density, allowing for greater storage capacity in smaller volumes compared to compressed hydrogen. This makes it an attractive option for applications where space is at a premium, such as aerospace and transportation. Additionally, liquid hydrogen can be stored for extended periods without significant loss or degradation, making it suitable for long-term energy storage needs. However, there are several challenges associated with liquid hydrogen storage. The process of liquefaction requires complex and expensive equipment, including specialized pumps, compressors, and cryogenic storage tanks. Moreover, boil-off, which occurs during storage due to the evaporation of liquid hydrogen, can be a significant issue, leading to energy loss and safety hazards. Despite these challenges, liquid hydrogen storage remains an essential technology for certain clean energy applications, particularly those requiring high energy densities and long storage durations. Solid-state hydrogen storage. Unlike compressed and liquid hydrogen storage methods, solid-state storage involves physically storing hydrogen in a solid material. There are several approaches to solid-state hydrogen storage, but they all rely on the ability of certain materials to absorb and desorb hydrogen atoms or molecules. One common method is metal hydride storage, which uses alloys such as titanium, zirconium, or magnesium to absorb hydrogen. When hydrogen gas is passed through the metal hydride material, it is absorbed and chemically bonded to the metal atoms. To release the stored hydrogen, the metal hydride material is heated or subjected to a reduction in pressure. Another approach to solid-state hydrogen storage is carbon nanotube storage, which utilizes the high surface area and absorption capabilities of carbon nanotubes to trap hydrogen molecules. This method is particularly promising for room temperature and ambient pressure storage of hydrogen. Several factors make solid-state hydrogen storage an appealing option for clean energy systems. Firstly, the stored hydrogen is chemically bonded or trapped within the material, eliminating the risk of leakage or explosion associated with pressurized gas storage. Secondly, solid-state storage systems can operate at ambient temperatures and pressures, simplifying the overall system design and reducing energy consumption for storage and retrieval. Finally, solid-state hydrogen storage materials can have high volumetric or gravimetric densities, making them suitable for applications where space or weight constraints are critical. Despite the numerous advantages of solid-state hydrogen storage, there are still some challenges that need to be addressed before it can be widely adopted. The storage capacity of current materials is relatively low, and further research is needed to improve the efficiency and durability of the storage medium. Additionally, the cost of certain storage materials, such as carbon nanotubes, can be prohibitive, although prices are expected to decrease with advancements in manufacturing technology. Solid-state hydrogen storage holds great promise for future clean energy systems and remains an active area of research and development. Factors to consider in choosing the right technology when selecting a hydrogen storage technology for a particular application. Several factors must be considered. Cost, safety, efficiency, scalability, and environmental impact are some of the most important aspects to evaluate. Each technology has its own cost associated with it, not only in terms of the initial investment for hardware, but also for maintenance and operation. Safety is another crucial consideration, as hydrogen storage involves handling a highly flammable and potentially explosive gas. The chosen technology should minimize the risk of leaks, explosions, or other accidents. Efficiency refers to the overall energy efficiency of the storage and retrieval process. The system should be able to store and deliver hydrogen with minimal energy loss. Scalability is an important factor for large-scale energy storage applications. The chosen technology should be able to scale up to meet the required storage capacity without significant cost or performance trade-off. Finally, environmental impact is an essential consideration, as hydrogen storage and utilization should not introduce new environmental problems. The technology should be environmentally friendly and sustainable. By carefully evaluating these factors, we can determine the most suitable hydrogen storage technology for a given application, ensuring a safe, efficient, and sustainable clean energy system. Conclusion: hydrogen storage plays a vital role in harnessing the full potential of hydrogen as a clean and efficient energy source. The various storage technologies discussed in this guide offer distinct advantages and disadvantages, and the choice of the optimal technology depends on the specific application and environmental context. Compressed hydrogen storage is a well-established and cost-effective solution for many clean energy systems, while liquid hydrogen storage provides higher energy densities for applications where space is limited. Solid-state hydrogen storage offers unique advantages such as improved safety and ambient operating conditions, but requires further research to enhance its storage capacity and material efficiency. By understanding the characteristics of each technology and the factors influencing their performance, we can make informed decisions about hydrogen storage and contribute to the development of efficient, sustainable, and environmentally friendly clean energy systems. As hydrogen storage continues to evolve, we can expect to see advancements in existing technology and the emergence of new materials and approaches that further improve the safety, efficiency, and scalability of hydrogen storage systems. These innovations will play a crucial role in driving the adoption of hydrogen as a clean energy carrier and revolutionizing the way we power our world. Thank you for joining us on this journey of discovery as we explore the exciting world of hydrogen storage and its potential to transform our energy future. If you enjoyed this guide and learned something new, please do not hesitate to give us a like and share it with your friends and colleagues who might also be interested in this topic. Your support and engagement help us continue creating valuable content and reach more people passionate about clean energy and sustainable development. If you have any questions, comments, or suggestions, feel free to leave them below. We love hearing from you and value your input. And if you haven't already, hit the subscribe button to stay updated on our latest content and join our growing community of clean energy enthusiasts. Together, we can drive the transition to a more sustainable future powered by innovation, knowledge, and a passion for a cleaner, greener world. Thanks again for watching, and we'll see you in the next video.
So now, a bit about me. My name is Mike L., and I am an experienced electrical engineer who has worn many hats, holding key roles in projects, engineering, planning, operations, asset management, maintenance, and field resources development. I design and pioneer engineering solutions to propel the utility and energy industry forward. My passion within the industry has also driven me to develop educational materials for the new generation of utility and energy professionals. The knowledge I teach is not only based on my own experience within the power utility industry, but also on knowledge gaps identified by other professionals in the field. Learning from me will provide you with the comprehensive, fundamental knowledge you need to kickstart your professional career in the utility industry. If you are interested in what I have to teach, check out my courses at Udemy and connect with me on LinkedIn, X, and Facebook. Don't forget to comment, like, and subscribe this video. Bye for now.